So now that you are safe to be in the lab, let's begin doing science. You should all know the answer to number 1 so far. Scientists follow a general outline of steps that are referred to as the scientific method. I'm just going to put scientific M. The first step of which depends on who taught you. You were either taught that the first step is to question or to hypothesize. Both are correct. So the first step is to question or hypothesize. There are 2 types of observations. Okay, you've probably learned this, you might have forgotten, but if you look down at number 5 and 6, it kind of gives you a hint. My 2 types of observations are qualitative and quantitative. Qualitative and quantitative. Science requires both kinds of observations, and in labs, you will use both in order to collect your data. Looking at the definition of qualitative, it involves words, verbal analysis, descriptions, and logical deductions. Part of your homework will be to come back and write down some examples. Okay, for quantitative, it involves numbers, math, and exact relationships. Your homework there would be to come back and fill in those. The way that this works, anytime I give you an amount of space to write, that's how much I want you to write. So in this case, I gave you a full 1.5 lines, fill in that 1.5 lines. So to summarize this, generally, when we make quantitative observations, we call these measurements. So quantitative observations, we call these measurements. Your hint to remember qualitative and quantitative. Qualitative is the quality of something. If you are describing something, how nice a sweater is. Okay. Quantitative is the quantity of something. How much of it is there? Qualitative and quantitative. Now we're going to switch topics from qualitative and quantitative to measurements. When you switch topics, you should switch colors. The reason for that is part of your memory is visual memory. By switching colors, you're giving your brain a signal, this is a new topic. Store this in a separate part of my brain. It makes it easier to recall, easier to understand. So for measurement is a type of quantitative observations. They include 3 pieces of information: the magnitude, which is the amount, the unit, and some part of uncertainty. Now, measurements are not numbers. A lot of the time, you'll do calculation with measurements and just give me a number as an answer. Measurements are not numbers. A number is obtained by counting. It is exact, and it is what we use in math. Measurements are obtained by comparing an object with a standard unit. Comparing an object with a standard unit. For example, an inch. At some point in history, somebody decided that this long is a foot. If I break this long into 12 even pieces, each one of those even pieces is an inch. That is all that an inch is. Someone at some point said, this is a foot. They made a model of that foot distance, and everyone made a copy of it. Put a piece of wood beside it, cut it off at the exact same length. Okay? It's just a standard unit, but we use it in our day-to-day life. So we use a lot of standard units. Measurements are inexact, and it is what science is based on. So if I was to take 3 tablespoons of sugar, and Vivian was to take 3 tablespoons of sugar, and we spent the next year of our life counting every single crystal in those 3 tablespoons of sugar, they wouldn't be the exact same number of crystals, right? A measurement is just a standard unit. We would probably be thousands of crystals off from one another. Okay? So keep that in mind when we're dealing with measurements. So the first part of measurement is the magnitude. That's easy. That's the actual number. The second part is the unit. A unit is a quantity that is chosen as a standard in which to compare other quantities. So the inch is a unit. Units are crucial for this course. When you give an answer to a problem, if you only give a number, it is only half right, and you will only earn the points for half of it. The units are just as important. So you will find, especially in this class, that these units are important. Whenever you record a measurement, you must record both the number and the appropriate unit of measurement. Based off of that, what do you think the phrase "no naked numbers" means? There's 2.5 lines there. Fill in 2.5 lines for what you think. So why are units important? Well, a very important example of this would be back in 1999 with the Mars Climate Orbital. Several countries worked together to create this Mars Climate Orbital, funding it together for $327 billion to make this orbital. It gets all the way to Mars, goes through the atmosphere 100 kilometers short, and is completely obliterated. Never takes one picture, is entirely useless for history. The reason was because one of the computers that they were using in America that was doing the calculations for the travel was doing all of its units in miles, because in America we do miles. But when they sent those calculations to the company in Europe that was actually programming the trajectory into the Mars orbital, well, in Europe they don't use miles, they use kilometers. So when they saw the numbers, you just automatically assume it's in kilometers. Who would put it in miles? So they put the trajectory into the system in kilometers. The math was done in miles, which means over the distance of thousands of miles getting to Mars, the orbital came in 100 kilometers short, which made it go in too fast, too hard through the atmosphere, and was completely obliterated. All right, units are very important, and sadly, this is not the only example of this. Many, many times in history, units have really messed up some calculations with different, especially when it comes to war things, it's really bad as well. Test yourself and try and answer these questions for your English units quiz. For uncertainty in measurement, why is there uncertainty? Well, measurements are performed with instruments, and instruments cannot have an infinite number of decimal places. For AP, I have a scale that measures out to 4 decimal places. It costs $1,300 and can only be used in certain labs. When you go to college, you can find some that go out to 5 and 6 decimal places. Those start going in about the $10,000 range. Okay, the more decimal places it has, the more expensive it is, the harder it is to create, the harder it is to calibrate. And that inability to have a ton of decimal places, that inability to be exact in your measurement is where that uncertainty comes from. Okay? Therefore, we must analyze measurements for accuracy and precision, and no, these are not the same thing. We're switching topics to precision versus accuracy. Switch colors. So for precision versus accuracy, accuracy is a foundational goal of science, is to seek truth and avoid error. So accuracy in science refers to the closeness of an experimental value to the true or accepted value. If we did a lab where I wanted you to find the mass of carbon, the accepted value for carbon is from the periodic table, and it is 12. If you did a lab and you got your mass to come out as 12.2, then you're pretty darn accurate. You're pretty darn close to that accepted value. If your mass came out to 20.1, you're not very accurate, right? You're nowhere close to that accepted value. So for accuracy, if we take multiple measurements, then we need to average them. Okay? And the accuracy of a value can be calculated as percent error. You already did that in one of your labs, and we'll cover that again tomorrow. Your summary will be part of your homework. For precision in comparison, the word precise is often used incorrectly as a synonym for accuracy. In your day-to-day life, people usually use accuracy and precision as meaning the same thing, but they don't. Precision is quite different. Rather than comparing to an accepted value, values are compared to one another. So precision refers to the repeatability of an experiment. And you need at least 3 data points. If I'm going to compare them to one another, I need at least 3 data points. So if once again I was trying to find the mass of carbon, and I got 20, 20.1, and 19.9. All 3 of those data points are really far away from the accepted value of 12. They're definitely not accurate, but they are close to one another, right? 19.9, 20, and 20.1 are very close to one another. So I'm being very precise, but I'm inaccurate. So let's look at a visual for this below. So if I was to be precise, but not accurate, this would be a good visual representation for this. All 4 of these represent a dartboard. For a dartboard, our goal or our accepted value is to hit smack dab in the middle. So therefore, if I'm being accurate, I hit right in the middle. If I'm being accurate and precise, all of my points hit exactly in the same spot in the middle. If I'm being accurate but not precise, then on average, I'm hitting that point in the middle. But each data point on its own is not hitting each other. They're not close to one another. So this is not precise, it's imprecise, but it is accurate. If I'm precise but inaccurate, then all my data points are close to one another, but they're not close to the goal. The same thing would be if I was hitting all of my data points right out here on this side, way on the wall. I'm playing darts and hitting the wall in the exact same spot over and over again. I'm really darn precise. I'm really bad at darts, but I'm really good at being precise, right? And then if I'm inaccurate and imprecise, then my data points are just kind of all over the place and not near the goal. So let's go through the breakdown of this. For precision, precision is reproducibility. If you have poor precision, it's from poor technique. So poor precision is called a reproducibility error. It is an error on the ability to get the same results. You can't reproduce the same results. So you have bad reproducibility. You have bad precision. For accuracy, accuracy is your correctness. How close are you to the goal? How close are you to the given value? Poor accuracy comes from poor procedures or equipment flaws. And if we have poor accuracy, we call this a systemic error. There's an error in the system in how you are collecting the data. If your scale is weighing a 10-gram weight as 11 grams, there's something wrong with your system. There's something wrong with what you're using. Your homework is to complete those first 3 half pages. Any blank in the whole packet should be completed, and make sure you highlight that SI system paragraph and answer the questions as well.